Hello, ladies and gentlemen, and welcome to the Continuous Insulation webinar. I'm J.R. Babineau, a building scientist here at Johns Manville. Thank you all for joining us today. First, a few housekeeping notes. Should you have any questions that come up during the presentation, please type those in the box on the little console on the right side of your screen, and we'll go through all those at the end of the presentation. Also, a recording is being made of this webinar, and it will be made available online, and you'll be getting an email later letting you know once this has gone live. So with that, we're going to get started. So in commercial and residential construction today, continuous insulation is really no longer the exception. It's really becoming the norm. As the International Code Council here in the States and the National Energy Code for Buildings in Canada and other organizations set ever higher energy efficiency requirements, and as just the industry in general continues to recognize the role the building enclosures play in overall building performance, continuous insulation, or CI as it's known, is often being used in conjunction with traditional insulation methods to help prevent thermal bridging. So today, as an overview, we're going to first define what a thermal bridge is and the different types of thermal bridges that are out there in our buildings and what their impact is. We're going to define what continuous insulation is and its role. We're going to look at various CI applications and how they can impact other building systems. And finally, we're going to compare different products. And in particular, we're going to highlight the continuous insulation products offered by Johns Manville. So continuous insulation as a concept has been in use, honestly, since the early 1900s, when ice houses were insulated on the interior with cork sheets. And more recently, CI has seen widespread use on low-slope roofs since the 1940s. But today, our focus is going to be for continuous insulation on exterior walls. So just real quickly, Johns Manville currently offers two types of continuous insulation. We have foam plastic sheathing and exterior spray polyurethane foam. Polyiso is a closed cell foam which brings with it a very good R value of about R6 per inch. Polyiso boards, in addition to being used as CI, can also create an air barrier and a water resistive barrier if the seams in the boards are taped and penetrations are sealed. Polyiso can be used above or below grade. JM offers two different brands of foam sheathing, our AP foil-faced foam sheathing and our CI Max foam sheathing. Both of these products use a Polyiso foam core. AP foil is most often used on the exterior of buildings, like in the upper photo of the slide. On the interior of a building, AP foil has to be covered with an approved thermal barrier to meet fire code requirements. Our CI Max product, however, has been engineered and tested and is specifically approved so that we can leave it exposed on the interior of buildings without a thermal barrier. CI Max comes with either a plain white or a plain silver side without any printing to provide a nice, clean, visible surface. The other type of continuous insulation offered by Johns Manville is our Corbon 3 spray polyurethane foam that can then be installed on the exterior of a building. Corbon 3 is JM's premier closed cell spray foam and provides an R value of 7 per inch. Corbon 3 provides air sealing and is approved by the Air Barrier Association of America to provide both air sealing and a water resistive barrier. Corbon 3 CI has been tested for fire resistance, and we're going to cover a lot of these in more detail later on in the webinar. Finally, our Corbon 3 product really provides excellent yield and has a wide window for install conditions, which is going to be really important if we're installing on the outside of a building. So to get started to really talk about the need for continuous insulation, we need a couple of definitions. Both ASHRAE 90.1 and the Energy Code defines continuous insulation as insulation that's continuous across all structural members without thermal bridges other than fasteners and service openings. And it can be installed on the interior or exterior and is going to be or could be integral to any opaque surface of the building envelope. For thermal bridge, neither the code or ASHRAE officially define what a thermal bridge is, but for our purposes today, we're going to use this definition that we have above. So a thermal bridge is really any element in a building assembly with relatively higher thermal conductivity than the surrounding materials, which is going to allow heat flow to bypass the thermal insulation. And a good example of that would be the infrared image on the left. So here, thermal bridging is what lets us see the pink framing, the warmer framing showing through on that second-story wall. So the most common thermal bridges that we have in buildings, just like what we saw in that previous photo, are through the framing. And these are really the main elements that are addressed by any code requirements we're going to find for CI. Steel is really the most obvious offender, but wood framing also can hurt wall thermal performance. And in a typical framed wall, the framing can easily account for up to 25%, and honestly even more, of the total wall area. So on this slide, the drawing here of the motorcycle engine helps illustrate another good example of thermal bridging, and that's through structural elements of the building. The cooling fins on this engine take the excess heat that we generate while the engine's running and let it help to reject that heat very efficiently to the outside air. If we were to look at this building, though, we might think, if we didn't know how buildings were built, that with all of these cooling fins, this building must produce a tremendous amount of extra heat that we need to get rid of. And certainly if we look at an infrared image of a similar building, we see that this is exactly what these extended balcony edges do, right? These extended floor slabs work great to take any interior heat and reject it to the outdoors. So structural elements like balconies and slab edges are really common thermal bridges, and they can be very effective at taking heat out of the building and rejecting it to the surrounding air. And the result is that we end up with high heating costs and also very cold floors. To kind of help reinforce this just a little bit more, right, wood, concrete, and steel can all form thermal bridges because they all conduct heat much better than insulation. So for comparison, wood is about 3.5 times more conductive than fiberglass insulation. Concrete is about 35 times more conductive than fiberglass, and steel is 1,400 times more conductive than fiberglass. So now let's look at a couple of examples that show the impact of thermal bridging from both wood and steel framing. And I promise this is the only slide in the webinar today that has anything even resembling math in it. So we're not going to go into any technical rabbit holes. But what the table shows is how we can account for framing in a typical wall construction following ASHRAE calculation methods. The numbers in the tables are all R values except for the next to the last row, which has what we call U values, and we'll talk about that more in a second. And what the method lets us do is treat the framing areas of a wall and the cavity areas of a wall separately, and then later take an area-weighted average of the two to determine what the overall performance is. So as we work from top down in the table, from the outdoors to the indoors, we start off with an air film, which gives a very small amount of insulating benefit. Then we have exterior cladding, and of course this number could really vary widely depending on the materials that are used. In this example, right, we're not using any continuous insulation. Then we next have our exterior sheathing, which would be exterior gypsum board, plywood, OSB, any sort of material like that we'd put on the outside of a building. Next would be the framing. In the two examples we have here, we have wood 2x4 wood studs on the left columns, and on the right-hand columns we have 3 5/8 light gauge steel studs. Next we would have our R13 cavity insulation. That would be something like a fiberglass bat. And then finally we've got interior gypsum board finish and an interior air film. So what we do for each wall area, for each section, we simply add up those R values that the layers provide. And then for the overall performance, first we have to convert those R values to a U value, which is called thermal transmittance. U value basically equals 1 over the R value, and vice versa. when we have to first convert to the U values at this step, because this lets us account for the fact that the heat going through this wall will actively look for and take the path of least resistance. So once we've done our area-weighted average as U value, then we can calculate the overall an effective R value, which makes this easier to really see what the impact is of the thermal bridging. So then if we look down at the bottom, we can see that thermal bridging through the wood framing and the wood frame wall isn't too bad, with the overall assembly performing at about R12 when we've installed R13. Through the steel framed wall, however, we see a really large impact because they are so much more of an efficient thermal bridge. The wall performance in this case is reduced down to about R8 when we designed and installed something that would be closer to R13. So the insulation in the steel stud wall is still doing its job, but the steel framing allows heat to flow around it and thus overall hurting the overall performance. So thermal bridging doesn't just impact energy use. It can also severely impact comfort and even indoor air quality in a building. Thermal bridging can lead to cold spots on walls and floors and in corners, at window frames, behind furniture, and even in closets. These spaces tend to get little air circulation, and the furniture or clothing inside closets actually acts as additional insulation. Condensation in these spots can easily form, and that can even lead to mold growth inside of our buildings, and so none of that is good. So the solution to all of these thermal bridging problems is continuous insulation, and there are many types of materials available. Foam plastic sheathing is mainly made from either polystyrene or polyisocyanurate foams. Closed-cell spray foam, as we mentioned before, can also be used as continuous insulation, and other materials, such as mineral wool boards, can also be used as continuous insulation. And so while all CI materials are important, not all CI materials are created equal. The table that we have on this slide compares some key properties of different CI materials. So as we work our way down the rows from top to bottom, start off pointing out that foam boards can often be used as a drainage layer to help keep rain out of our walls, so long as these materials are paired up with tapes for the seams and sealants for any penetration. Exterior spray foam doesn't need any tape, but it may still need flashings around windows and doors. Mineral wool boards will drain water, but they actually do still need a separate drainage layer to keep water ultimately out of the wall. All of the materials listed can be used below grade. Water vapor permeability is one of the areas where materials can vary widely. Polystyrenes tend to be more water vapor open than spray foam or polyiso foam, but in general, thicker foams of any type will end up having a lower water vapor permeability. Finally, mineral wool boards are extremely water vapor open, as we can see 110 perms, and these differences between materials can ultimately drive other decisions in how a wall system might be designed. Next, the ability to act as part of an approved air barrier system is also critically important. Different products carry different levels of testing and approval. It's really important to look for products and systems with Air Barrier Association of America approvals, as these products will have passed through a rigorous set of tests that will include install details for a successful project. R value, of course, would be another important area where materials can vary. Installing a particular R value with one material versus another can change the thickness of the wall system. And some foam sheathing boards can actually resist wind loads without any additional exterior sheathing. But again, you need to look for manufacturer's assembly test data. And finally, all foam plastic CI materials have to pass fire code requirements, and we'll dig into that more later. Actually, we're going to talk later in more detail about drainage for rain, air leakage, condensation control, and fire resistance. So in this table, the CI materials offered by Johns Manville, if we recall, are polyiso foam and exterior spray foam. So these materials, as you can see, all have the highest R values available of any of the materials listed. and can all provide drainage, air barrier, and vapor control functions. Later in 2017, JM will be launching a mineral wool CI board as well, which will add this vapor open and fire resistant material to our continuous insulation portfolio. Just to compare the materials a bit more, there's really several key distinctions that we can talk about between polyiso foam sheathing and extruded polystyrene, or XPS. And the table that we have on this slide lists many of the items highlighted by PEMA, which is the Polyiso industry group. We're going to look at just 3 of those in our webinar today. The first is R value. Polyiso has one of the highest available R values of CI materials. Johns Manville's Polyiso products provide R values of about 6 per inch of thickness. Higher R value is important because it allows the project needs to be met with thinner CI material. Using a lower R value CI results in overall a thicker wall system, which can impact fasteners, cladding attachments, fastenings, windows and doors, and angle supports. Fire resistance is another key distinction. In a fire situation, polyiso foam forms a char layer but remains solid, whereas polystyrenes can soften and melt and even potentially drip burning liquids. Finally, polyiso is not affected when it's exposed to solvents or adhesives or coatings, whereas many polystyrene materials can be aggressively attacked and even dissolved by petroleum-based materials. So all important things to consider when choosing different materials to use. So before we move on, we're going to review just real quickly some of the benefits, right, of using continuous insulation. Using CI in a project is going to help well beyond just meeting the needs of the energy code. By preventing thermal bridging, CI reduces energy loss, which in turn reduces heating and cooling costs. Preventing thermal bridging also reduces condensation risks in walls and therefore increases wall durability. And again, as we've mentioned, many CI materials can also act as air barriers and drainage layers. So next, we're going to look more closely at applications, how we're going to use CI materials. So as we were focusing on today, really on walls, continuous insulation can be installed on really a wide variety of wall types. On the exterior of walls, CI can be used over wood framing, steel framing, pre-engineered metal buildings, and masonry walls. Of course, on the exterior is typically where we usually think of using CI, but it can also be used on the interior. Metal buildings are a good example of where we can use CI on the interior, where it could be left exposed to the occupied space, but of course it still then needs to meet fire code requirements. The example on the left would be Johns Manville CI Max product. So in an application like this, where we have a warehouse, where inside this warehouse we have a cold storage room. So CI on the interior is a great solution, and CI Max in particular is a good solution because it can be left exposed. In this case, in the photo, a matching tape is all that we really need to create a well-sealed and insulated assembly. And of course, we can see in the photo, they've put a white tape on the face of this plain white board, so you get a pretty good clean look overall. For masonry buildings, CI can also be installed on the interior. And actually, interior continuous insulation is often needed, especially for retrofit work on historical buildings where we have to preserve their outward appearance. Of course, in these situations, careful consideration has to be given by the designer to make sure that all of the effects on things like old brick are taken into account. The photo on the right shows JM's AP foil faced foam sheathing on the interior of a concrete block building, in this case a house in Florida. This approach allows things like stucco or other claddings to be directly applied to the block on the exterior, and the furring strips on the interior are for the gypsum board. So AP foil, remember, must be covered with a thermal barrier, such as gypsum board, to meet fire code requirements. When it comes to energy conservation code compliance, how much continuous insulation is required depends on where we're building. The map here illustrates the different climate zones used by the IECC code and ASHRAE Standard 90.1. Basically, the higher the climate zone number, the colder the climate, the more insulation we're going to need. over time, the Energy Conservation Code has added more and more requirements for continuous insulation. And what this table shows on the slide kind of is a march through time of different code versions. If we just consider steel-framed walls, and if we start back at the 2006 version of the Energy Code, continuous insulation was really only required in what we would call cold climates, zones 5 and above. This would be like cities like Denver, Chicago, Boston, Minneapolis. In 2009, the code increased the CIR value requirements in the cold climates and then extended where CI was needed all the way into climate zone 2, which is what we would consider a warm climate. Climate zone 2 would be cities like Houston or Phoenix. In 2012, the code further increased the CI requirements even into climate zone 1, which would include Miami, Hawaii, or Puerto Rico. These requirements were maintained in the 2015 and even the 2018 versions of the Energy Code. Essentially, any steel frame commercial construction needs to include continuous insulation unless the designer uses a performance or trade-off method to show code compliance. If we just look at the 2015 IECC code, like we have a summary of on the slide right now, the common theme to notice is how across all kinds of different climate zones and across all wall types, continuous insulation is called for in the prescriptive tables. So clearly, the code recognizes that CI is a critical component for all code-compliant building envelopes. So we've talked about how CI can control condensation by reducing thermal bridging in cold spots. And the building code also recognizes that if we add CI, we reduce the condensation risks inside the wall, and so the code will allow a Class 3 vapor retarder, which is typically just latex paint, to be used in many cold climates instead of requiring a Class 1 or 2 vapor retarder, which would typically be polyethylene sheets or craft-faced cavity insulation. But to qualify, there's a minimum amount of CI required, and that depends on the climate and the thickness of the wall. An important point to note is that in some cases, especially in climate zone 6 and above, the CIR value requirement for condensation control could actually be higher than what's required by the Energy Code. This is really a problem that the designer has to deal with, but it's something that shouldn't be ignored. The requirements listed in the table that we have on the slide are actually also present in both the International Building Code, which covers commercial construction, and the International Residential Code for homes. So as we talked about earlier, foam sheathings and exterior spray foam can both be used as water-resistive barriers and air barriers. Foam boards have to be combined with tapes and sealants, and all the materials need to integrate with window and door flashings to be able to do this. An example would be the photo on the right. Really, the important thing here is to look for assemblies that have Air Barrier Association of America, or ABAA, certification. Both Johns Manville's AP foil-faced foam sheathing and our Corbon 3 spray foam products have passed all of the testing required for ABAA approval, and our websites have got all of those certifications and details. Wind resistance testing can also demonstrate how foam sheathings can be used without an additional exterior sheathing. And by additional exterior sheathing, here we mean things like exterior gypsum board or OSB. So as with air barrier performance, always look for system level testing from your manufacturer. The photo that we have here in the slide shows an example of only 1 inch thick AP foil-faced foam sheathing mounted to a 20 gauge steel framed wall. So this was actually our air leakage test system, and this system was tested for air leakage across a range of increasing air pressures. And at the very end of the test, we ended up with an air pressure that was equivalent to a 200-mile-an-hour wind. So as you can see in the photo, there's a little kink in those steel studs. The wall itself buckled, at which point we stopped the test for safety reasons. But it's important to note that the foam boards never broke and the tape seams never failed, even at this really high air pressure. For foam plastic, fire code is a key consideration, and for foam plastic continuous insulation, one of the primary fire tests we all have to pass is called NFPA 285. This is a required test for any wall systems with foam plastic on types 1 through 4 construction. And basically, construction types 1 through 4 are considered non-combustible versus type 5, which would be wood frame construction. The NFPA 285 test is required not only for foam plastics, but also for combustible air barriers, combustible cladding systems, as well as foam plastic insulation. So you should see these sorts of tests published for house wraps, just a wide variety of combustible materials. The NFPA 285 test is a system level test, which means it includes everything from the cavity insulation and the framing all the way out to the exterior cladding of the building. Again, Johns Manville's AP foil, foam sheathing, and Corbon 3 products have test reports for all of these tests, and the reports show basically a large table with all of the approved system combinations. So we've touched on this before, but it really does bear repeating that sheathing materials perform differently when exposed to fire. Thermoset plastics, again, such as Polyiso and closed-cell spray polyurethane foams, char and tend to stay intact during fire exposure. Thermoplastic foams, such as polystyrenes, can soften and melt and can even drip burning liquids in a fire situation. Finally, mineral fiber, though, is non-combustible, and so it really provides the best fire performance of all CI materials. When it comes to installing continuous insulation, the devil is truly in the details. Whether CI materials are used as water-resistive barriers or air barriers, or if we're just going to use them for their thermal performance, they change the way a wall system is built and require careful detailing. The responsibility for these details lies with the designer, but there are resources available from Johns Manville, the ABAA, and also the Foam Sheathing Committee that provide excellent resources to help answer these questions. So to help bring everything together, Johns Manville has developed the JM All-Purpose Wall System. This system has been designed and tested and combines our AP foil face sheathing with various options for cavity insulation, fasteners, tapes, and cladding systems. And because of our high-pressure air leakage testing, the system can even be used without additional exterior sheathing, which could be an option to reduce cost and wall thickness. And while we recommend using the tapes and sealants to deliver drainage and air barrier performance, tapes can also be omitted, and the system could be combined with more traditional methods such as building wraps or coatings. The all-purpose wall system includes many installation details and helps to deliver a successful project. So now that we're getting down to the end, let's first summarize again and compare the various Johns Manville insulation products that we've learned about. JM currently has 3 CI products available. That would be our AP foil face foam sheathing, our CI Max foam sheathing, and our Corbon 3 spray foam. Corbon 3 provides the highest thermal performance of R7 per inch, and it also provides air barrier and WRB functions with at least 1 inch of thickness and vapor control with at least 1.5 inches of thickness. As exterior CI, a Corbon 3 can be installed up to 3.5 inches thick, kind of per our NFPA 285 fire approvals. JM's foam sheathings are available in a wide range of thicknesses and R values, from R2.7 up to R28. AP foil faced foam sheathing, like spray foam, has to be separated from the occupied space, but CI Max, remember, is approved to be left exposed, which can be really useful for interior applications. All of our foam sheathing products can also be excellent air barriers and vapor retarders if the board seams are taped and penetrations are sealed. And your JM Territory Manager can provide recommendations for tapes that work well with all of our foam sheathings. Finally, remember, we will be launching a mineral wool CI board coming here in 2017. And as a teaser, there'll be webinars to cover that in more detail when that product launches. In addition to the products that we have, JM stocks our AP foil and mineral wool at all of our fiberglass manufacturing facilities. And CI Max is produced in all of our Polyiso plants, and again is available with either a white or a silver facing that doesn't have any printing on it, and also in extended sizes to fit your needs. The JM Advantage puts what you want to order on one truck to maximize your inventory, service your customers across a number of product lines, and stock jobs more efficiently. So to finish, today we've learned about different types of thermal bridges and what kind of impact they can have from both an energy perspective and things like comfort and indoor air quality. We explored the different types of continuous insulation and their properties. We talked about energy code compliance with continuous insulation. And we looked at the thermal benefits of CI, or not only the thermal benefits of CI, but what other functions CI can deliver, such as managing air, water vapor, condensation risk. And we examined fire code considerations for CI and the importance of good installation. In closing, though, we'd really like you to remember that Johns Manville is your source for the most complete line of building insulation products and expertise. And with that, our webinar is over. My colleague Gina Carosa is here, and she's going to help us go through any questions that have come in over the course of the webinar. Gina?
Hello, everyone. Thank you for joining us. The first question we have is, our value is usually tested at 75 degrees Fahrenheit. My XPS foam rep says that as temperature drops, like it would here in the Northeast during the winter, the R value degrades for these products. Is this true?
So the R value for polyiso foams has been shown to change a little bit as temperature goes down. I mean, this is a good question. It's something that in the building science community we've been working on. It's been discussed now for the last several years. What we have found is that even though this does happen, the temperatures where this would be a really significant impact is even in Canada, even in extremely cold climates, the impact is very small. So I would say on one hand, yes, it's something we're aware of, and as a manufacturer, we are working to address. But from a practical standpoint of does this impact your building today, I would say overall no. It's really a very small impact. Good question, though.
Next question. Back to page 28, I see dense glass in the assembly based on the picture. If there was no dense glass, could CI Max replace the AP foil in that application and pass NFPA 285? Competing manufacturers have recommended their Class A ISO board in this application.
So we have not run that exact test, but given the fire test for a material to be left exposed. The fire test that CI Max had to pass it's a completely different fire test, but in terms of severity, I would argue that it's worse than the NFPA 285 test because we actually have claddings and other things that get placed in front of that. So in a hypothetical situation, if we were to go tomorrow and test this with no exterior gypsum board and CI Max instead of the AP foil, I would say yes, it should pass. We didn't because in this situation, you could just use AP foil, right? We could remove the exterior gypsum board. It could be just AP foil over the steel studs. That has already passed the NFPA 285 test. So from which product would you use? It makes more sense to use the AP foil. It's a lower cost product because of this application, because it's exterior.
Is JM working to retest to get a 4.5 R30 board like other manufacturers? If so, when?
That is a good question. I know we are continuously looking to tweak and improve the performance of our products. I would say that would be a question that we can circle back around to our product management and product engineering team and get you an answer offline.
Why has JM's AP foil been able to accomplish the NFPA 285 without the gypsum and others have not?
That's a good question. I guess I have not looked in detail at competitors' test reports, but I know that we were able to. So we didn't really dig into the exact technical reasons of why we were successful, other than that we simply were. So that's certainly a question that we could follow up on, but I don't have a good answer for that right off the top of my head today.
Can foam sheathing be used both horizontally and vertically in the same application?
So on the exterior of a building, yes. Right, you could use foam sheathing on a wall, under a soffit, under an elevated floor. That's not an issue. When it comes to leaving something exposed, I know at least our CI Max product is approved for it's what's called walls or ceilings. And so if we were going to wrap the inside of a room in it, you wouldn't be able to do that. But again, the applications that we encounter for that tend to be extremely uncommon.
Does JM sell tapes and fasteners?
So JM doesn't, let me back up. We do sell a fastener for our AP foil system to go with the all-purpose wall system. Let me jump back down here to the questions slide. We do not directly sell tapes. We have, again, for the all-purpose wall system, we have a specified tape that your territory manager can kind of help, put you in contact with a distributor for. And then for CI Max, we have identified recommended tapes that will match the surface finish of both the white and the silver CI Max boards. Again, your territory manager can kind of direct you to those, though.
And lastly, it looks like, can JM foam sheathings be used below grade?
Yes, they can. JM's AP foil, Polyiso can be used below grade. This is something that we're kind of working on getting that message out there, because there's some historical wisdom, I think, that is suggested that Polyiso can't really be used below grade, but in particular, the foil-faced materials we use for sheathings can be used below grade just fine.
Thank you, JR. That concludes our question portion of the program. You will receive a survey following the webinar, and we would appreciate it if you would take a little time to offer your feedback on the webinar today. Additionally, if you have any questions that you are unable to ask, you may submit them via the survey, and we will respond to you directly via email. Please also indicate in the survey if you need a certificate of completion, and we'll email it out directly to those who respond. Finally, we will be posting a recording of this webinar online, so if you missed any part of the presentation, or if you would like to view it a second time, you'll be able to access it online. We will be sending out a link to that as soon as we have it posted. Otherwise, we thank you for attending today and hope you enjoy the rest of your week. Thank you.